Hey everyone, in this video we are going to continue our discussion about input-output organization from the previous video. We'll talk about serial versus parallel data transfer. Then we'll take a look at three main modes of data transfer, namely programmed data transfer, interrupt initiated data transfer, and DMA, that is direct memory access. And then finally we'll conclude this discussion with an analysis of the input-output processor. So let's first start with serial versus parallel data transfer. All right. Now, in parallel data transfer, each bit of the message has its own path. And that's clear from the name itself, right? So each bit of the message has its own path. The total message is transmitted at the same time, which means that an n-bit message must be transmitted through n separate paths. So each bit takes one separate path. All the data is thus transmitted at the same time. So naturally, this mode of data transfer is fast because the entire message is transmitted in one go. It's also expensive because you need as many data lines as there are bits in the data to be transmitted. And this is used for short distances where speed is important. So if for your application speed is more important than money, then you'll pick parallel data transfer. The other alternative is serial data transfer. So in serial data transfer, each bit in the message is sent in a sequence one at a time. All right, so only one transmission path is used and all the bits are going to be transmitted one after the other serially. So naturally, this method of data transfer is cheaper. It's cheaper because there is only one transmission path needed, and it's slower because all the data bits must then take this single path to reach the destination. So it takes a long period of time, especially if the message has more bits. Now, the serial data transfer can be of two types, synchronous or asynchronous. In synchronous serial transfer, two units share a common clock. Then bits are transmitted continuously at the rate dictated by the clock pulses. In asynchronous serial transfer, on the other hand, binary information is sent only when it is available, right? The line remain idle. Otherwise, now let's take a look at serial asynchronous data transfer. Like we discussed in the previous video, most of the times the kind of data transfer occurring within a computer system is asynchronous, right? Because different units are controlled by different clocks. So the data transfer is not synchronous, but rather asynchronous. All right, so in case of serial asynchronous data transfer, each character that is being transmitted consists of three main parts. There's a start bit, which is always 0. This start bit, as the name implies, is used to indicate the beginning of a character. Then after the start bit come the character bits. This is the actual message that we are sending. And after the end of the last character bit is the stop bit. These are always 1. All right, so the start bit is always 0, the stop bits are always 1. Now, this is a diagrammatical representation of this kind of transfer. So earlier, your line is here, and then there's a start bit. Like we said, it's always 0, so the start bit becomes 0. And then there are the character bits. These are all the character bits. And then there are the stop bits at the end of the message. Now let's talk about baud rate. Baud rate, as it's an important characteristic of serial asynchronous data transfer. So baud rate is defined as the rate at which serial information is transmitted. That is the rate at which serial information is transmitted. So you'll notice that it is equivalent to the rate of data transfer in bits per second. Right? For instance, if a terminal has a transfer rate of 10 bits per second, then for the transmission of an 8-bit message, the data transfer rate is 110 baud. So it's measured in bauds. All right. And how did this 8 become 11? It's important to understand. If a terminal wants to send 8 bits of data, the total bits transmitted will be 11. 8 bits for the actual data, 1 start bit, and there are generally 2 stop bits. So this is important to understand when numericals come into the picture, right? You might be asked to compute baud rate for a given transmission setup. So you first have to understand how many bits are actually being transmitted. When we're talking about serial asynchronous data transmission, right? So the actual data that is sent is the given number of bits plus 1 start bit plus 2 stop bits, unless it is specified in the question itself how many stop bits are there, you have to assume 2 stop bits. So actually 8 bits will be transmitted, and for 8 bits at 10 bits per second, sorry, for 11 bits at 10 bits per second, you have the baud rate of 110. Alright. Now let's talk about the various modes of data transfer. So data transfer to and from peripheral devices is handled in one of 3 possible ways. We could have programmed input output, we could have interrupt initiated input output, or we could have direct memory access. Now out of these 3, we are going to focus on DMA the most. So we'll take a quick look at programmed and interrupt initiated IO, and then take a longer look at DMA. Alright, let's first start with programmed IO. Now, in programmed IO, so programmed IO operations are the result of the IO instruction being written in the computer program. So whenever we use the term programmed, alright, it stands for a computer code. Alright, so whenever something is programmed, it means that there is a pre-written computer code in place to perform that kind of operation. So when we're talking about programmed IO mode of data transfer, it means that input-output instructions have been written in the form of a computer program, and then each data item transfer is initiated by an instruction written in the program. That is, the entire thing, the entire data transfer is handled, controlled exclusively with this program that has already been written and placed in the memory. Now, data transfer under programmed control requires a CPU to constantly monitor the peripheral devices to see when a transfer needs to be made. So when we're talking about programmed IO, that means the CPU will constantly have to monitor all the peripherals attached to it to see if and when any of these devices require any kind of data transfer. Now, the application of this method of data transfer, programmed IO, is that it is particularly useful in small, low-speed computers or in systems that are dedicated to monitor a device continuously. Because remember, it's the CPU's responsibility entirely to keep an eye out on all the peripheral devices and to keep making sure be available whenever any of them needs any kind of data transfer, right? So it's only useful in small, low-speed computers or systems where you only have 1 or 2 peripheral devices. So it's entirely dedicated to those devices only. The limitation in programmed IO is that the difference in the data transfer rates of the CPU and the IO devices makes this method highly ineffective. Consider this, for instance. Consider a computer that can execute the 2 instructions that read the status registers and check the flag F in 1 microsecond. Alright. Also consider an input device that transfers its data at an average rate of 100 bytes per second, which is 1 byte per 10,000 microseconds. Now, in such a system, the CPU will have to check the flag 10,000 times between each transfer. And that's not an efficient use for CPU. CPU is what does everything inside a computer system. So if your CPU is spending this much time just to keep an eye out on all the peripheral flags, just to make sure that no one needs its immediate attention, all right? So it has to keep checking every peripheral device over and over again, all right? So that's not an efficient use for your CPU because CPU has other things to do. So this is a highly ineffective method overall. So now we move on to the second kind of data transfer method, which is interrupt initiated IO. Alright, now programmed IO wastes a lot of the CPU's time, as you've already noticed, because the CPU stays in the program loop until the peripheral device indicates that it is ready for data transfer. The CPU has to keep checking it over and over again. All of this can be avoided by using an interrupt facility. Alright, what happens is, in interrupt initiated IO, the IO interface monitors the peripheral device. So each interface will monitor the device to which it is connected. When that device is ready for data transfer, special commands are used to issue an interrupt request signal to the CPU. So the CPU will go about its normal operation like it does. The IO interface will keep an eye out on the peripheral device to which is attached. When that device is ready for some kind of data transfer, the input-output interface will interrupt the CPU. Right? Upon reception of such a request, upon the reception of an interrupt, the CPU momentarily halt its current task and it will branch to a service program that is designed to process the IO transfer. So simply stated, the CPU will pause whatever it is doing, it will go handle the interrupt, all right, and then after the completion of the IO transfer, after completion of whatever data transfer that specific device needed to do, the CPU will then return to its original task. This is a much better method than programmed IO. So instead of having the CPU repeatedly keep checking all the flags of all the peripheral devices to see if someone needs some kind of data transfer, the device that needs any kind of data transfer will issue an interrupt signal through the interface to the CPU. CPU will go about its normal business, and when it receives such an interrupt, it will pause its current operation for a moment. It will go check out the device, what it needs, it will take care of that data transfer, and then after the completion of that side job, it will come back to its main task. So a much better utilization of CPU's time. The third kind of data transfer is direct memory access. Now, transfer of data between a fast storage device and memory is often limited by the speed of the CPU. See, CPU is what does everything, all right? So, speed of the CPU dictates the speed of the data transfer. So, even if you have a very, very fast storage device, it's not going to matter because it will all be dictated by the speed of the CPU. So, if you could remove the CPU from this equation, you could significantly improve the speed of data transfer, all right? If CPU weren't a part of this entire data transfer operation, things could go much faster, especially if you have a very high speed device. Now, this kind of transfer technique is known as direct memory access. So, the device is directly now able to access the memory, right? DMA is a feature that allows the IO interface to transfer data directly in or out of the memory independent of the CPU. You have taken the CPU out of the transfer equation, and now the memory and the device through the IO interface can communicate with each other directly, right? So this is what happens diagrammatically. Now, in programmed IO and interrupt initiated IO, this is what's happening. CPU is in the middle of everything, right? So between if there's a data transfer that has to occur between a certain IO device and the memory, CPU is going to be involved in each and every step. It all has to go through the CPU. CPU will do everything. In DMA, what you've done is you have given a common bus access to the IO. The IO can now communicate directly with the memory. CPU is on the sideline, all right? And by taking the CPU out of the equation, you have now created a much more faster and efficient system. So the CPU is now free to take care of all its other responsibilities because it does have a lot of other stuff to do, right? So the CPU can keep doing all of that, and the IO device is now free to access the memory directly. For that, a DMA controller is needed, which we'll talk about in just a brief moment. Now, direct memory access. So in DMA, the CPU is involved only in the beginning and the end of the transfer. Only 2 times during this entire data transfer is the CPU going to be involved, in the beginning and in the end. So in the beginning, CPU is the one that initiates the transfer by supplying the interface with the starting address and the number of words needed to be transferred. All right, so CPU initiates the process. It gives the IO interface a starting address of the memory from where the memory words are going to be accessed and the number of words that need to be accessed. All right, and in the end, after the data transfer is complete between the IO interface and the memory, CPU is notified via an interrupt that the transfer is now complete. So these are the only 2 times that a CPU is involved during direct memory access. Now let's talk about the CPU bus signals required for direct memory access transfer. So there are 2 main bus signals required, BR and BG. BR stands for bus request. It is used by the DMA to request the CPU to relinquish controls of the buses, right? Because when data transfer has to take place, the IO interface, the peripheral device, needs access to the buses, and the buses are usually under the control of the CPU. Unless someone else requests them, they're generally with the CPU. So the BR request line, the bus request line, is used by the DMA to request the CPU to relinquish control of the buses. BG, bus grant, this is used by CPU to intimate to the DMA controller that the buses are in high impedance state. So high impedance state means that the buses are now free to be used. CPU no longer has access to the buses. The CPU is no longer going to use the buses. It has relinquished control of the buses to the DMA controller. These are what BR and BG lines do. Now, BR and BG are used by the CPU and DMA controller to coordinate the uses of the buses, right? So, the one using the buses, either the CPU or DMA controller, the one that is currently using the buses to transfer data in or out of memory is called the bus master, right? So now we have two options. So either the CPU could be using the buses or the DMA controller could be using the buses. Whichever one is using the buses at the moment is known as the bus master. The bus master initiates the transfer, and all the other participants in the transfers are called the slaves. So through bus arbitration mechanism, what we're trying to say is we can have two bus masters. When we're talking about direct memory access, we can have two bus masters. Usually there's only one. Usually only the CPU is in charge of all the buses. But during DMA, through the bus arbitration mechanism, through BR and BG lines, we can have two bus masters. Now, when DMA is the bus master, because this is what we're going to look at. So normally CPU is in charge of the buses, but now since we're talking about direct memory access, let's see what happens when DMA is the bus master. Now there are two ways the DMA controller can communicate with memory for data transfer, either through burst transfer or through cycle stealing. So let's see what these two mean. Burst transfer versus cycle stealing. So in burst transfer, a block sequence consisting of a number of memory words is transferred, right? So entire chunk of memory words is transferred. This is needed in case of fast devices where data transmission cannot be stopped or slowed down and until an entire block is transferred. So we're not going to transfer the data bitwise now. Entire chunks of memory will be transmitted one chunk at a time in bursts. That's why it's called burst transfer. The other option is cycle stealing. So what happens in this case is cycle stealing allows the DMA controller to transfer one word at a time, one memory word at a time, after which it must return the control of the buses to the CPU. So what's happening is the DMA controller is allowed to transfer only one word, and after this transmission it has to give back the control to the CPU. And then if it wants to transmit another word, it will have to take the buses again request for the bus. The CPU will then relinquish the control to the buses, and then the DMA controller will transmit one more word, and then it will give back the control to the CPU. So it goes in cycles. Why it's called stealing? Because it's like it appears as though the DMA controller steals one memory cycle from the CPU every time it needs to transfer a word, right? Alright, now this is what a DMA controller looks like, and we are going to talk about all of these components individually. Let's first start from this side. We have three main registers here, as you can see: address register, word count register, control register. The address register contains addresses of the desired location in memory. So whichever memory location this device needs to access, that address is placed in the address register. Then there's the word count register. It keeps tracks of the number of words to be transferred. Control register specifies the mode of transfer, whether this data needs to be written or read. Then we have DS and RS. DS, DMA select, and RS, register select, are used by the CPU to select registers in the DMA, used by the CPU to access DMA's registers. Now when BG is equal to 0, that is when bus grant is 0, CPU can read or write from or into the DMA registers using the data bus. When BG is equal to 1, CPU has relinquished control of the buses, and then DMA controller communicates directly with memory. Alright, DMA request and DMA acknowledge, again these are important lines. These are used by DMA controller to communicate with peripherals according to the handshaking mechanism. So handshaking mechanism we have already discussed in the previous video. Both DMA request and DMA acknowledge lines are used by the DMA controller. So the request line comes from the device to the DMA controller. This line is used by the IO device to indicate to the DMA controller that this device now needs to access the memory, either to read something from the memory or write something into the memory. When DMA controller receives some kind of request from any IO device, it sends out an acknowledge signal to indicate to the device that its request has been received by the controller. Alright, let's talk about DMA initialization. DMA is first initialized by the CPU by sending the following information through the data bus. So like we discussed earlier, even though CPU is not involved during the process of direct memory access, CPU is involved during the very beginning of the process and in the end. Right? So the initialization is actually done by the CPU. So this is how it's done. So the CPU, what it does is the starting address of the memory block where data is available for reading or from where data needs to be written is initialized by the CPU, right? Another information that is given by the CPU is the word count, that is how many memory words need to be accessed. Number 3, control to specify the mode of transfer, whether this data needs to be written or this data needs to be read. This is also indicated by the CPU. And finally, a control is given by the CPU to the DMA controller to initiate the transfer, right? So these 4 things are done by the CPU at the very beginning of any DMA transfer. And this is the block diagram of a typical direct memory access transfer. So let's see what's going on in this diagram. We have the 4 main components involved in a typical DMA transfer. We have the CPU, we have the memory, we have the DMA controller, and we have the input-output peripheral device. And now you can see the device is connected to the DMA controller. The DMA controller is connected to the CPU, and through this bus it is connected to the memory as well. And the IO device is also connected to the memory, again through this intermediate bus, through the data bus, through the address bus. Now let's see how the different components work. See, first, both RD and WR lines in this case are bidirectional, that is read and write. Both read and write lines are bidirectional, right? Because the direction of the transfer depends on whether CPU is the bus master or the DMA controller is the bus master. So these lines have to be bidirectional. See, when BG is equal to 0, read and write act as input lines. That means CPU can communicate with the DMA registers. CPU can have direct access to the DMA registers when BG is equal to 0. When BG is equal to 1, read and write lines act as output lines, allowing the DMA controller to communicate with RAM. So you see how the flow of data from input to output depends on whether CPU is in charge of the buses or DMA controller is in charge of the buses. Alright, CPU initializes DMA through data bus, right? Once DMA receives the start control command, it starts the transfer between peripheral device and memory. When peripheral device sends a DMA request, DMA controller activates the BR line, CPU responds with the BG line, right? The DMA controller receives a request from an input-output device. It sends a BR line, it activates the BR line, bus request line. This line goes to the CPU. When CPU receives the bus request line, it activates the bus grant line to indicate to the DMA controller that the bus access to the bus has been granted. Alright. DMA then puts the current value of its address register into the address bus, initiates the read or write signal depending on whether this device needed the memory for reading or writing purposes, and then it sends a DMA acknowledgement to the peripheral device. So once it gets the access of the buses and after it places the address of the desired memory location into the address bus, after that it acknowledges to the IO device that direct memory access can now occur, and you see this direct memory access can then occur between the device and the memory without any interference from the CPU. Now, when a peripheral device receives the DMA acknowledgement, it puts a word on the data bus or reads a word from it. Right? So once it gets the acknowledgement signal, it can then directly communicate with the memory. It can either read or write whatever it needs to do. After each word is transferred, the DMA controller increments the address register so as to move on to the next address in the register, and it also decrements the word count register because now one of the words has been transferred, so the counter must be decremented right? The word count must be decremented. If there were 100 words, now there are only 99 words, and then only 98 words would be left, and 97, and so on. All right, so the counter has to go down. So as long as the word count is not 0, so as long as there are still words that need to be transferred, the DMA controller will keep checking the DMA request line. And once the counter gets to 0, when all the words that needed to be transferred have been transferred and the word count is now 0, the DMA controller stops all further transfer and it removes its bus request line, right, by interrupting the CPU. It indicates to the CPU that the transfer is now complete. So when the CPU receives the interrupt, it reads the contents of the word count register just to make sure that the count is 0, because the count of 0 would indicate to the CPU that the transfer was completed successfully. Now, this checking of the word count register can actually happen at any time. CPU is free to check the contents of the word register at any time to keep an eye out on the transfer, how the transfer is proceeding. Now, a DMA controller may have more than one channels, right? So in this diagram, for the sake of simplicity, we were considering a single peripheral device. But this DMA controller is actually connected to all the peripheral devices that are connected to the system, right? So it usually has more than one channel, because at a given time your system typically has more than one peripheral devices attached to it. So in that case, each channel has its own pair of request and acknowledgement line, right? So if we had more peripheral devices attached to this DMA controller, we would have the requisite number of request and acknowledgement lines, right? Then each of them would have their own address registers and their word count registers. So priority can be established then accordingly. According to the speed of the devices or the urgency of the data transfer, the DMA controller can then assign priority to all of the devices attached to it. But the overall process of transfer remains the same. It remains the same as the one that we just discussed. All right, finally, this is the last topic for this video as well as this unit, I/O processor. So let's see what I/O processor is. Now, input-output processor. See, instead of having each interface communicate with the CPU, a computer may incorporate one or more processors and assign them the task of communicating directly with all peripherals. So usually what we do is, we saw in the previous video corresponding to this topic, that for each peripheral device there is a separate interface, and each of these interfaces then communicates with the CPU. So instead of doing that, a computer can also it can combine one or more processors and give them the exclusive task of communicating independently with all the peripherals. So instead of having multiple interfaces, what we're saying is we have a single interface, a single designated processor. Now, an input-output processor, IOP, may be defined as a processor with DMA capabilities that communicates with IO device. So what we have done now is, instead of having multiple interfaces communicating with the CPU and the peripheral devices, we have assigned a single processor or a group of smaller processors and designated them as the IO processor, right? So this IO processor now, it's like a DMA. So it behaves like a DMA controller, and it has the capability to communicate with the IO devices independently. All right, diagrammatically this is what it looks like. So now what we have done is, this is the memory, this is the CPU, these are the peripheral devices that are connected to the system. Instead of having an interface here for each independent peripheral device, instead of doing that, we have combined them all together into a single IOP. We name this input-output processor, and then this IOP essentially takes care of all the peripheral devices, and it has DMA capabilities. So this is what an IOP is. It's like a processor exclusively for peripheral devices. Alright, so it's important at this point to understand the difference between IOP, CPU and DMA controller, because they have a lot of things in common, right? So first of all, IOP versus CPU. So IOP technically is a processor, and CPU is also a processor. So what's the difference? See, an IOP is like a CPU, which is designed to handle the details of IO processing. So it's like a CPU, but it deals only with IO processing. So CPU will do everything, IOP will only handle the input-output devices. right? And now the difference between IOP and a DMA controller, because again we mentioned that IOP has DMA capabilities. So what separates an IOP from a DMA controller? Unlike a DMA controller that needs to be set up entirely by the CPU, an IOP can fetch and execute its own instructions, and this is how a DMA controller is different from IOP. You might recall that DMA controller, although it allows direct access of memory, it needs to be initialized by the CPU. So first it is initialized by the CPU, and then it goes on and does its entire processing independent of the CPU. And IOP, on the other hand, does not need to be initialized because it's a processor on its own. So it has the capability to fetch and execute its own instructions. It does not require any kind of initialization from the CPU. Now, let's talk about the IOP now. The data formats of peripheral devices differ from those of memory and CPU. We've already covered this. The IOP, therefore, must structure data words from many different sources, right? Because there's one IOP now. There are not different interfaces for each peripheral device. There is a single unit that is going to handle all the devices. That means it must be capable of handling the different requirements of these different devices. Now, data is gathered in the IOP according to the rates of transfers of different devices, as well as the bit capacity of the IOP itself, right? Because now you have to consider the rate of transfer of the different devices as well as the capacity of this processor itself. So the data is gathered in the IOP in accordance with all of these conditions while the CPU is executing its own program. So the CPU is a separate entity now, right? Now, after all the data is assembled within the IOP, it is transferred directly into the memory by stealing one memory cycle from the CPU. So it's like this: the IOP will gather all the requests that all the devices have, right? All the data transfer requests, and then when it is done, when it is full, it cannot accept any more requests for any devices. It will steal one memory cycle from the CPU. You remember cycle stealing? So it will steal one memory cycle from the CPU. It will transfer all that data into the memory directly, and then now it's empty, and then it will start accepting data from its devices again. So this is how an IOP works. Now let's see how CPU, IOP and memory communicate. So the communication between IOP and the peripheral device is similar to program control method. The communication between IOP and memory is similar to DMA, similar to direct memory access. Now the communication between IOP and COP is a bit more complicated. It depends on the level of sophistication of the system. In very large scale computers, each processor is independent and any of them can initiate an operation. The CPU initiates all operations, but all the IO instructions, which are also known as commands, are executed by the IOP, right? So depending on the level of sophistication of the system, this is how IOP and CPU communicate. The CPU will initiate all operations, but all the operations pertaining to IO will be dealt exclusively by the IOP. Alright, that's it for this video and this unit as well. So just a quick recap. We discussed serial versus parallel data transfer. We talked about three main modes of data transfer. We talked about programmed IO, interrupt initiated IO and direct memory access. Finally, we took a look at input-output processor.